Hey guys, we're going to work on some free fall problems. We talked about free fall last time. So if you recall, this is when things are moving up and down on the y-axis. Now, because things are going to be moving up and down, usually in a gravitational field, it's usually Earth. And so the acceleration of gravity on whatever planet it is usually called little g. And so in a lot of problems, people will substitute the a for a little g, not only in the chart, but also in their formulas. And I don't care. You can do that or not. It doesn't matter to me. So here's a problem. Let's take a look. So how do the steps work when we work problems? It's a word problem. It has words in it. First thing I do is I relax. I've got my coffee. I'm in a nice quiet space. I'm ready to work. I am focused. Okay. I'm relaxed. Breathe. Read the problem. Read it twice. Have a mental picture of what's going on. You may want to underline or highlight things that are important. From rest is important. 50 meters above the ground. Okay. Next, we draw a picture. So here's our little picture here. Okay. Now maybe this isn't a picture you want to draw. Maybe this is too much work. So let me show you one that I think is a lot faster. So here's a picture I drew real quick. It can be as simple as this. You're going to drop something from a height. Our height here, I believe, was 50 meters. If you let something go, if you just release something, if you drop something, the initial velocity is always going to be 0. So the question is, what is the final velocity when it gets down to the bottom? Now I know what some people are thinking. Sharky, it's going to be 0. And I can't argue with the fact that once it gets down to the ground, it makes contact with the ground. The ground will exert an equal and upwards force on it, and it will come to a stop, and I agree with you. But if you've ever had something heavy dropped on your foot, when that thing is released and it gets down to your foot, you know that it's moving because it strikes your foot and it hurts. So we don't care about what happens after it hits the ground. We care about what happens just a split second, a split of seconds before it gets down there. That's our final speed. That's what we want to know. So here we go. Read the problem, draw a picture. Now I'm going to make a chart, try to populate my chart. I'm going to go ahead and have it already populated. So when I hit the button, there it is. Initial, final, A and T, X naught, B naught. What are things you can put into your chart right away? Well, A, which sometimes people will call little g, you can put this right away. If you're on Earth, this will be negative 9.8 meters per second Now, the minus sign. Minus and plus signs are important. They mean direction, and you have to be consistent in what you do. What I do is anything that is acting down or is moving down, is going down, that has a minus sign. The force due to gravity pulls us down. So it has a minus sign. Anything going up, acting up, has a plus sign. Okay. Now the initial velocity is going to be 0 because you're dropping it. The final velocity is what we want. What is its speed just before it hits the ground? I need to interpret those words as I'm looking for final velocity. And I put a question mark because I want to know where I'm going. If you don't know where you're going, you can't solve the problem. Now, the hard part is knowing where to put this height. What does that mean? So, what you do here is kind of up to you. What I've said is that the origin I have down here. So I'm saying x final is 0. So this down here, when the ball gets down here, that's 0. And I say x initial is up here where the person released it. So I'm saying going up would be positive. And it really doesn't matter. It's up to you as whether you're going to call that negative or positive, or whether you're going to call this 0, call this negative 50. You can do that. It's purely up to you. And as you do more of these, you'll get better. So I made my chart. I've got some stuff. I know where I'm going. I'm looking for final velocity. So now what I do is I look at my 3 kinematic formulas and I choose one. I choose one that'll work. I choose the easiest one. There may be more than one. A lot of people don't like the fact that there's no time. And so first thing they'll do is they'll spend all this time looking for time. They'll go, oh, I need the time. The question mark is over here on VF. It's not on time. You may not need time. There's one equation that doesn't have time in it that'll work. It's equation number 3. Okay. VF squared equals VI squared plus 2A delta X. This is equation number 3, and it's been solved for VF. I just use equation number 3 because I don't need time. So, equation number 3, I'm going to plug in my numbers. This is 0, 2, G. This should be delta Y. Of course, it's Y because we're in the Y-axis. And what I've done here, G is negative 9.8. And when I take my X final of 0, final is down here, initial is up there. 0 minus 50 is negative 50. What happens is these two minus signs cancel. So there's something advantageous about the way that I did this, how having this 0 and having this at 50, is that I can then get rid of these two minus signs and I get a positive answer. Right, because you try to take a square root of some negative number and it ain't going to happen. So I should get about that speed. Now once I know this, I can plug that into my chart. It's known. Okay. Now there might be a second part, usually is. How long does it take to reach the ground? So now we're looking for t. So what I can do is take this 31.3, chuck it in here, and I can solve for t. Now that you know just about everything in the chart, you can use any equation you want. Usually the simplest one is the best, so I could use equation number 1. And that's what I did. I used equation number 1. Now remember, instead of A, I'm calling it little g. This is equation number 1, and I solve for time. Take a look at equation number 1. See that this is it, and I'm just solving for t, and I can get t. Okay, so this is the progression that I use when I do problems. Let's do some more. Okay, here's another one. Now instead of dropping something, we're going to be throwing something upwards. We're going to be launching it straight up. And so these are a little tricky because now things will change. So I relax, read, I can draw a picture, and of course I can have a very simple picture. Maybe it's not something like this, but so my picture could look something simple like this. I'm launching something into the air. Now let's get this straight. If you throw something up into the air, the initial velocity is not 0. Right? If I was going to throw something upwards, and my initial velocity is 0, then the thing would just sit in my hand wouldn't move. Right? We care about that split second when you're throwing something upwards, when the thing, whatever it is, a ball, right, just as it leaves the palm of your hand. So this will not be 0. At the maximum height, though, your velocity at the tippity top is going to be 0, because what does it do? It goes up, 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 up. It slows down as it goes, and at some point up there at the top, it's going to stop. So what do? I read, maybe I highlight some things. Height of 20 meters, so that height would be 20. We want to know what speed it's thrown with here. At the highest point, at its maximum height, right, VF equals 0. So what they're telling us here, it rises to a height of 20. They're saying that that's as high as that thing gets, 20 meters. So that's the max height. It's not going up any higher. If that's the maximum height, then it's going to stop at the very tippity top. I'm going to make a chart. Here we go. I'll populate my chart. Remember this little a. I can call that little g. At the very tippity top, my final velocity is going to be 0 up here at the top. My initial, I don't know. That's what I'm trying to find. So I screwed this up. I need to have a what there? I need to have a question mark because I got to know where I'm going. Here again, I don't know time, and that drives people nuts. They're like, oh, I need to solve for time, but you may not. Okay. So you look at what you have. You look at your list of formulas. Which one would you use here? Well, here again, there's one that doesn't have time in it. It's equation number 3. What I'm going to do is I'm going to rearrange equation number 3 and solve for initial velocity. Here's my final. Okay. So I rearranged this and I've solved for V initial. And what happens is the plus sign here becomes a minus sign, right? And so square root of this stuff, I'm going to plug things in. Okay. So my final speed is going to be 0. My g is negative 9.8. Now y here, this should be delta y. I should have a little delta here. Okay. So in this problem, what I ended up doing is I ended up calling my initial position 0. My final position was up here at 20. I called that positive 20. And here again, it kind of depends on you and what you want to do. Okay, so on this last problem, right, we had this was 0. This was 0. This was 50. So we said it starts here at 50 and it ends up down here at 0. So we ended up with a negative 50, right, to cancel out that negative sign in front of the 9.8. And then for this next question, I'm saying, okay, I'll call this 0. I'll call that positive 20. So what happens is I'll get a, when I do x minus x naught, I'll get 20 minus 0, which is 20. Okay. I plug all that in. I should get around 19.8. Thankfully, all my minus signs cancel. You'll find that even if they don't cancel, you know, if you just make it positive, take the square root, you'll get the answer most of the time. It will work. But yeah, these two things drive a lot of people crazy, right? Do I call this 0 and I call that positive 20? Should I call this 0 and call that negative 20? Technically, it doesn't matter. You need something that'll make your math work out. So I try to make it so that I don't have any negative signs when I have to take my little square root here. Okay, here's one that's a little tricky. Stone's thrown straight upward with a certain speed. It's caught on its way down at a 0.5 meters above where it was thrown. So it goes upwards. It'll stop somewhere at its max height and then comes back down. And it's caught 5 meters above where it was thrown. Let's try to draw a picture. So let's say it starts at a 0 point at the ground, whatever. Maybe this is your hand, and you throw it upwards with a speed of 20. So initial velocity is 20. It goes up, 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 up. At some point, it's going to get to a max height. Its V final up here will be 0. But then the thing comes back down, and it's caught 5 meters above where it was thrown. So it ends up right here. So it starts here and ends up here, right? And so this is the real displacement. Even though it went up and then came back to this point, we only care about from here to there. So this could be the picture that I draw. So with that picture, we can make a chart. I'll try to plug in some numbers. So my chart looks something like this. Right, we'll say that, well, okay. It started at the ground, it ended up 5 meters above the ground where it was thrown. Initial velocity was positive 20 because it was headed up. Acceleration is little g, and it's negative because it's pulling us down. All right, what equation could you use? I could use equation number 3 again. It's the only one that doesn't have time in it, and I could solve for that. You can see this happens a lot. Now the trick here is that since it's headed downwards, our velocity is really supposed to be a negative, right? And so we can just write it like that, or you can flip these around. Up to you.